So welcome everybody to our Colloquium lecture series. I'm very happy to have as our first speaker in the semester one of our own graduates, Laura Coyle. Laura is currently a senior optical engineer at Boyle Aerospace in Boulder, Colorado. She's also the principal investigator of the Ultra-Stable Large Telescope Research and Analysis Program. She did her undergraduate in physics at Colgate University and came here to do her master's and PhD. Laura is currently supporting NASA missions, also astrophysics programs. Part of those are the Operational Land Imager 2 and the James Webb Space Telescope. She's also a member of the Boyle Aerospace Wavefront Sensing and Control Team and responsible for on-orbit alignment and commissioning of the JWST. So, Laura, thank you for being here, and we look forward to your lecture.
Is this guy on? Doesn't sound like it. Is it on, Cindy? I'm good. All right. All right. Thanks for everyone for coming out this afternoon, and thank you for that introduction from Dr. Guzman. My name is Laura Coyle. I'm an optical engineer at Boyle Aerospace, and I'm here to talk to you about one of the projects that I've been working on recently, which is enabling the LUVOIR mission concept, specifically looking at optical systems engineering and technology development for the next generation of large space-based telescopes. If we can advance slides. So every technology development effort needs a roadmap. Here's mine for the next hour or so. So when we talk about enabling LUVOIR, this is a journey. We start with the need for ultra-stability. What does it mean, and why do we need ultra-stable telescopes in space? Then we move on to the first phase, systems engineering. That's defining our requirements and figuring out what technology gaps we have in the architecture. Then we move to phase 2. That's technology maturation of specific components, starting small with the building blocks. And then finally, phase 3, technology maturation of systems, starting to look at interactions and evaluating performance, not only at the component level, but also at the system level for final comparison to requirements. So starting with the ultra-stability need, I'm going to take a step back here and talk about the Astrophysics Decadal survey. So this is a survey that's run every 10 years by the national academies. And essentially what it is it's a report to NASA where there's consensus among the astronomy community that says these are your priorities for the next 10 years. These are the types of missions that we think you should build, large, medium, and small, and this is the type of science that we think that you should go after. And so astrophysics has been doing this since the 1960s, and it's produced some really exquisite observatories over the last few years. The recent surveys have prioritized in 2001 what was at the time called the Next Generation Space Telescope, now known as the James Webb Space Telescope. You can see from the picture here, if you're familiar with how Webb looks now, there's been a little bit of additional concept development since this was first proposed. Then in the next decadal survey in 2010, the priorities for space were WFIRST, the Wide Field Infrared Survey Telescope, currently under construction, and for the ground, LSST, the Large Synoptic Survey Telescope, now renamed the Vera Rubin Observatory. And so here we are in 2020, and the question is, what is the national academies and the astronomical community going to recommend that NASA put its investment in for the next 10 years? One of the things they did a little bit differently this time around is they sponsored 4 science and technology definition teams, and each of those teams studied a mission concept with a specific science goal and an architecture in depth, such that they could provide reports to the national academies to say, these are the types of things you could build in a flagship class in the next 10 to 20 years. So there were 4 mission concepts that they looked at: LUVOIR, Origins, Links, and HabEx. I'm going to talk very briefly about them at the high level. So the first one, LUVOIR, up here in the top left corner, is a 15-meter segmented aperture telescope. And you can see they borrow a lot of the heritage from James Webb. They have this large sun shield, segmented telescope that deploys on orbit, and it's in this open configuration. The point of LUVOIR is to hunt for exoplanets, both to detect them and to do spectral characterization, and also to do just general UV, vis, and near-IR astrophysics. Another mission with a similar set of science goals is HabEx, the Habitable Exoplanet Observatory. And HabEx has a very different architecture. It's a 4-meter monolith that was designed for stability and ease of fabrication. And instead of having, or in addition to having an internal coronagraph, which is used to image exoplanets, it has this external occulter called a star shade. And so essentially what you're doing is you're using the star shade to block the bright light from a star so that you can see a dim planet next to it. This can be done either internally in a coronagraph or externally through the star shade. Moving away from the UV vis near IR bandwidths, LINX is an X-ray telescope, so it's going to study energetic phenomenon. And instead of the sort of primary mirror reflectors that we think about. X-rays are too energetic to reflect off those types of mirrors, and so you have a bunch of grazing incident cylindrical shells. And LYNX has quite a lot of heritage from Chandra, but it'll have better sensitivity through its larger effective area and also improved SNR on the detectors. Finally, on the other end of the spectrum, we have the Origin Space Telescope. So that's a 6-meter segmented telescope that's going to be looking in the far infrared. And the thing about this telescope is that in order to be sensitive at those very long wavelengths is it has to be cold, in this case about 4.5 Kelvin. So each of these telescopes, because they're doing different science that requires a different architecture, has a different sort of tall pole technical challenge. For LYNX, it's making all of these concentric shells very well and aligning them. For HabEx, the telescope is actually fairly low risk, but this free-flying star shade needs to be aligned very well and also has very tight fabrication and cleanliness requirements. For Origins, the thermal control system is its tall pole, getting to that 4.5 Kelvin and maintaining that temperature. And for LUVOIR, it's keeping this large 120 segment primary mirror phased to enable its exoplanet science.
How far is that shade from the telescope?
It's like, what is it, 100,000 kilometers, something like that. So they're actually less worried about the formation flying. This has been proven on things like LISA Pathfinder with microthrusters and the GRACE follow-on missions. And so it's actually the shape of these petals needs to be stable to sort of the tens of micron range. And also they have to worry about individual specks of dust diffracting light into the telescope. So it has to be extremely clean. All right. So one of the really exciting things that two of these missions enable is we actually might be able to answer the question, are we alone? Find an Earth-like exoplanet in the next 20 or so years, if we build a capable observatory. That's always the key. So for the design reference missions, both for LUVOIR and HabEx, they've looked at their observing scenarios, they've looked at their sensitivity and their underlying technology, and they've both determined that with 5-ish year missions, they should be able to detect an Earth-like exoplanet with 95% certainty. There's a bunch of statistical assumptions that follow that, but based on what we know with data from Kepler and from TESS, we know that there's a lot of exoplanets out there. We know that there are a good fraction of them that are in the habitable zone of their star. And so even if some small fraction of them are truly Earth-like, we'll have enough statistical sampling, especially with LUVOIR and even with HabEx, to be able to do some of that characterization. So the instrument that enables this for LUVOIR and partially for HabEx is a high contrast coronagraph. And a coronagraph is simply an instrument that blocks the light from a bright star so that you can see the dim planet next to it. And at a very simple level, the way that it works is you have on-axis light from the from the star, and off-axis light from the planet. You bring that collimated light from those very distant sources to a focus, and you put a small opaque mask right there called the focal plane mask. That blocks most of the planet, or most of the starlight, lets the planet light through. Then at another pupil plane, you insert a Leo stop, and essentially what that does is cleans up the rest of the diffracted light from the host star that isn't taken care of by the focal plane mask. So that's a very simple first-order description of it. But as you can imagine, for these very large segmented observatories, the design of the coronagraph is very specific to the observatory and has a lot of complex masks and other control elements that are needed to give it the contrast that you need. And actually, there was a question out there for a while that could you even build a very high sensitivity coronagraph for a segmented aperture? 10 years ago, they didn't think it could even be done. And they've answered that question, but the problem is that you need masks that look like this. And so you can imagine with modern photolithography processes, you can start to write these very complex patterns with very fine features that's needed to control the diffraction from these segmented apertures like LUVOIR, in order to, again, block the light from the focal plane and eventually create an annular region called the dark hole that has about 10 billion to 1 contrast. So you're looking for a Earth-like planet that's 10 to the 10 times fainter than the star next to it. There's something about a lighthouse and a firefly, but I believe that this is many orders of magnitude beyond that. So that's what we're aiming for. We're aiming for 10 billion to 1 contrast on a 15-meter observatory that's segmented in space. So you spent all of this time developing your coronagraph technologies, optimizing the design, and you need to make sure that the telescope that's feeding the light into the instrument isn't messing up your very carefully defined diffraction suppression scheme. And so typically what coronagraphs will do is they have some active elements built in. Usually they have a series of at least 2 deformable mirrors that can change shape dynamically and can correct for errors that are happening in the rest of the observatory. So usually what happens is you'll have a reference target, a bright star that you slew to. You'll use the high flux from that star and the good sensitivity you get on the detector to shape your deformable mirrors to correct for whatever the telescope's doing. Then you slew back over to your target star and you take your observation. And you continue that chopping pattern back and forth. And so the job of the telescope is to stay stable during that time in between your reference targets. And the level that you need to maintain that stability in order to keep this 10 billion to 1 contrast in the dark hole is something like 5 to 10 picometers RMS for a 15-meter segmented space telescope. It's very difficult. JWST stability is in the nanometer class. So you're talking about 4x the area and 1,000x the magnitude. So people have sort of known that this level of requirement has existed for a while. And in terms of specifying telescope stability for large apertures that are segmented, there's this notional requirement of 10 picometers per 10 minutes. That's the allowable amount of wavefront drift. And so just given that very coarse kind of rule of thumb, we know that we are going to need active and adaptive wavefront sensing and control that are several orders of magnitude beyond the state of the art, moving from nanometers to picometers. So this ultra-stable large telescope research and analysis program is moving down the path of answering that. So phase 1, systems engineering. What Ultra is doing is what we did in the past is perform a 1-year design and modeling study of large segmented apertures like LUVOIR. And the key objectives of this were to look at not only what's happening spatially within the telescope, which some other people had looked at previously, but also what was happening in the temporal domain. You need to be looking at these in that 2D space in order to make sure that you're not over-specifying performance, you're not making things harder on yourself than it needs to be. We also needed to look at what disturbances we can ignore at the nanometer level that might start to be important at the picometer level and that might have to be budgeted going forward that we ignored previously. Then looking at all of those requirements and all of the pieces that we need to control, what are the technologies that we have available to solve each of these problems? And then given the current capabilities of those technologies, what do we need to develop? Where do we have gaps? And how are we going to move forward to close those gaps? So luckily, as I mentioned, these mission concepts had been studied in detail over the last 4 years, and so we did not come at this in a vacuum. There were studies performed by those teams, by NASA Center engineering teams, and some previous industry-funded studies and internal research and development. So we had this fairly broad base of both architecture, systems engineering, and technology pieces to choose from when looking at how are we going to enable this 10 picometer per 10 minute stability. And so then as all good systems engineering's efforts start, you have top-level contrast and wavefront error stability budgets. So this is what's guiding the needs for all of the technologies flowing down through each of the subsystems throughout the architecture. Then once you have allocations at the subsystem level, you sort of know what all the pieces need to do. You have trade studies. What are the potential ways we could approach this? Then you plug in those capabilities, look at how the error budget flows back up. And of course, as you mature your models, as you develop new technologies, as you understand more about the coronagraph requirements, this is really an iterative process, especially at this phase where it's really in concept land and we have a lot of knobs to turn. It's really about what's the balance between all of these things that's going to make this build feasible. And then finally, the output of this study was identifying the final technology gaps. Once we've done our best job of rebalancing, where do we still have room between the capability and the allocation from the error budget, and then the roadmap. How are we going to close those gaps? And we looked at a variety of areas across the architecture. We looked at what kind of perturbations we're going to have, both environmental and induced on the spacecraft, structural materials, things like joints and latches, how does the composite fit together, mirror materials and mounting, active segment sensing and control, beam walk line of sight, and control methodology. You're making all of these measurements and you have all of these active systems. How do you make them work together in a way that's most efficient? And the reality is that you start with sensitivities, simple models, and parametric analysis, and again, build your fidelity up from there. So looking specifically at LUVOIR, this is a sort of an optomechanical model of what we're dealing with. So we've got a 120 segment primary mirror. Segments are sort of on the meter class size. We have a secondary mirror that's out here, sitting tens of meters away from the primary. And then we have this sunshade back here. The JWST sunshade is sort of tennis court sized. This one is more football field sized, 50 meters on a side. And notionally, we know that we're not going to get 10 picometers per 10 minutes passively. So there's a whole active control system that's notionally wrapped around this telescope. And it starts with very slow systems, things like updating the deformable mirrors in the coronagraph, to very fast systems, things like looking at edge sensors on these mirrors and actuators so that you actually can control those at sort of Hertz level bandwidths, and laser metrology trusses between the primary mirror and the secondary mirror so you can keep all the optics locked in place. Because for something like 10 picometers, you need to make sure not only that the primary and the secondary mirror are aligned to each other, but they're aligned to the rest of the optics. So you can't just let the primary move and fix it with the secondary. You really have to pin both of them to their ideal locations to some degree. And so really, when you're thinking about systems engineering, it all starts with the requirements. And in this case, the requirements are driven by the coronagraph. And here's a couple of simulations on the left of what error on the primary mirror does to the contrast level in the coronagraph. So you'll see if you have a misalignment of the primary that manifests as coma, your dark hole is still pretty good. You don't get that much contrast degradation. But if you look at random segment motion, if all of those segments are wiggling around with respect to each other, the contrast degradation is several orders of magnitude. So what this means is that the coronagraph is more sensitive to certain modes than others. And that means that we need to worry more about controlling picometers on the segment level than we have to on the whole motion of the primary mirror. So not all aberrations are created equal. Segment level piston tip and tilt are the worst. The other thing that we can do is we can think about what spatial frequency perturbations we're going to have and what control loops we have available to fix them. So in this case, when we're talking about spatial frequency, it's things that are happening on the full scale of the primary, things that are happening on the segment level, and things that are happening mid or high spatials within a segment. And so you can imagine there's dynamics and there's thermal, and that's going to change both the sort of the global position of the primary mirror. It'll change the position of the mirrors with respect to each other. It may cause a little bit of warping. If you have a three-point mount, you might get a little bit of trefoil print through as the temperature changes on the back of the mirror. Same thing for the dynamics. The whole thing will vibrate, segments will vibrate. They're pretty stiff, so you don't get a lot of mid-spatial modes on the mirrors themselves, but it's possible you'll see something small. So you're going to get dynamic and thermal disturbances sort of across the spatial range. Knobs that we have to turn to control that. Speckle control is those deformable mirrors in the coronagraph. And if you get a high authority deformable mirror, so something that has a lot of actuators across the pupil, you can correct mid and high spatial frequencies. So the speckle control can go out to 20, 30 cycles per aperture, depending on your DM design. You also have something called a low order wavefront sensor. And what that does is it takes the rejected light from that focal plane mask, the light from the host star, and it uses that to say what are the low order Zernicke's happening in this. It's looking at the deformation of the spot size to identify power, tip, tilt, astigmatism, things like that. So in that case, you have control that's sort of on the order of a cycle or two per aperture. Those are the pupil level Zernicke's. Then you'll have thermal control. If you can keep everything really thermally stable down to the level of a mirror segment, then you know you're not going to get deformations from thermal. And then there's also active control we can reposition the primary mirror segment assemblies, so that's segment rigid body, and then damping and isolation can again also help reduce motions that are happening on the pupil and the segment level. So the regime that we have to worry about is a place where we know the coronagraph is sensitive, a place where we don't have that many control loops, and a place where we know we're going to have disturbances. And for this system, that's segment low order. Lots of control loops over here, not much perturbation out here. That's the place that we know that we have to worry. Okay, spatial frequency requirement, done. Temporal frequency, same thing. We know that we're going to be getting dynamic disturbances at all frequencies, especially at the mid to high. Thermal disturbances we know are happening a little bit more slowly, so we expect those to dominate at the low spatial frequencies. For the coronagraph, we talked about slewing to this reference star and back and forth. Well, another way to essentially help your telescope stability is if you're constantly making corrections during the cycle. So that would be something like adding another wavefront sensing and control loop. If you just let it drift over the course of a coronagraph observation, then you have to sort of control that drift to a really low slope. If you increase the amount of your active control, then it can drift by a higher slope amount because you're essentially kicking it back down every time. You're bringing it back to that baseline stable level. And so the control loops that you have here are similar to the ones for spatial, but they, again, operate at different frequencies. The speckle control with the deformable mirrors gives you really good spatial coverage because you have a lot of actuators, but you're not getting that many photons from the planet. Again, that's that 10 billion to 1 contrast. And so if you don't have that many photons, you can't run a correction very fast. So while this is very good spatially, it's poor temporally. You're only getting it every couple of minutes or so. Thermal control is the same thing. You can't push heat energy through glass very quickly, and so that, again, that's also moving a little bit more slowly. Damping really starts to come in at the high temporal frequencies, both passive and active, and isolators as well. And so here our region of concern is this quasi-static, this sort of hertz, tenth of a hertz regime, where again, we know that the chronograph is sensitive, we don't have that many control loops, and we know that there's going to be disturbances. So the segment level piston tip and tilt happening at about a hertz, that's where we know we need to have the picometer stability. And the systems engineering gives us that insight so that we can say, all right, when we're defining our technology components to enable that stability, these are the bandwidths that they need to work on, and we can let the performance relax outside of that. So in error budgeting space, you've probably seen something like this. This is a root sum square error budget where you have components that are flowing up to some top level allocation, errors combine in quadrature. That's really not a bad assumption for very complex systems, especially at the beginning where you're not going to be running high fidelity stop modeling. And you can use this to organize all of your perturbations, all of your subsystems. You can put active sensing and control loops in here as well. And this is a good way to track all of those allocations. And this is what was done for James Webb. So something a little bit new that we're doing for LUVOIR is we're moving to this matrix error budget. So rather than just thinking about the spatial scales, we're also thinking about the temporal scales. They did do this for Webb. It was it was a little bit different configuration. But here, since we're caring about things that are happening on seconds to minutes, and Webb really has stability requirements on hours to days, there's a little bit more granularity to this budget. So now we're talking about not just one top-level allocation, but the allocation as a function of spatial and temporal frequency. And you'll notice a couple things about these numbers, one of which is that the smallest numbers are over here in this high spatial frequency column. And that's actually an artifact of the way that it was modeled. So this assumption is a little bit too conservative. So I'm going to have you ignore that column for the moment. You'll notice that here when we have, this is these low temporal frequencies happening at the pupil and the spatial scale, you have some relief. You're talking about 20 to 80 nanometers RMS, picometers RMS, not 10. But down here at this mid-spatial, mid-temporal frequency, so that's again segments moving in piston tip and tilt on the Hertz time scale, this is where we have our tightest requirements. And that 10 picometers per 10 minutes, that sort of is a rule of thumb, it turns out, is really not that far off from our tightest requirement. But again, the point is that the whole system is more like maybe 160 picometers RMS, not 10. We don't need to make our job any harder than it needs to be. Another thing that we're doing is we're moving from this, this matrix approach that essentially bins the errors to a power spectral density-based error budget. And the reason for that is we can get even more granularity in those domains. And another feature is that it takes advantage of the fact that wavefront error is a single metric, but what we really care about is where is energy in the coronagraph dark hole ending up. So in a really simple example, if you were to have a pure sine wave error across your primary mirror, this is really not physically realizable in a segmented telescope, but if you had it, you would get energy that's distributed in two very specific parts of the coronagraph dark hole. If you had another sine wave error that was in the y direction, you'd get two spots here and here. And since those spots don't spatially overlap, you don't actually need to budget them to meet some top-level allocation. They don't interact, they don't work together to degrade the contrast. And so you can use this PSD approach to map phase error in your system to a spatial extent in the coronagraph dark hole and get some additional relief. So maybe now you're not talking about 10 picometers on something, you're talking about 15 or 20. And so an example of that is, again, we're going back to the segment level piston tip and tilt that are our most sensitive terms spatially. And if you look at where the energy ends up in the dark hole, if you take a slice through it, piston is very close to the inner working angle, tilt is shifted over a little bit, and then mount print through, primarily trefoil from thermal effects, is shifted over even more. And so if you were to just take these as whatever the contrast degradation was and root sum square them, each one gets 1 over root 3, about 50% of the top level allocation. But the fact that these peaks are shifted with respect to each other and you don't get maximums that overlap means that you get a little bit of additional relief. And now you're talking about each one getting 80% of the allocation. And when you're talking about picometers, having an extra picometer or two to play with could turn out to be really significant for the technology development. So this is the kind of approach that we're going to be implementing moving forward. All right. So systems engineering, error budgets, all of that, very important. Now what we're going to do is talk about the specific subsystems that we evaluated and what technologies we believe need to be advanced in each of those areas to enable this error budget that, again, rolls up to this top level 160-ish picometer RMS number. When you're talking about technology gaps, you need to classify them or group them because not all gaps are created equal and not all gaps have the same path to closure. So for the purposes of our study, we have 6 gap types. The first is a knowledge gap, and that really has to do with the fact that not that many people have made measurements of large space structures and optics on the picometer level. Physics tells us that we probably don't have any showstoppers extrapolating from nanometers to picometers, but we're not sure about that. So a knowledge gap is all about, we need to do more work in this area to figure out if there's some phenomena that we haven't accounted for. Then there's the low TRL gap, TRL meaning technology readiness level. So that's something that there's a scale from 1 to 9 that's used to classify how mature something is. 1 being, I drew it on a cocktail napkin, and 9 being, it's been flying in space for 10 years. And so when you're talking about technology development, TRL 2-3 is sort of like, yeah, I built this prototype, we did it in the lab, the physics works, the fundamental concept has been demonstrated. Moving up into 4 or 5, now you've done a higher fidelity simulation, higher fidelity hardware build and correlated simulation, starting to test things in a relevant environment. For space, that means thermal vac testing. And then once you start getting to TRL 6, 7, that's able to be incorporated in a flagship mission with fairly low risk. 7, 8, 9 have flown in space. So when we're talking about low TRL, in this case, we're talking about TRL 2-3. We have a concept. Maybe we have a hardware demonstration, but it really needs to be developed to show that it's feasible in this application. Mid-TRL is, we think that we've shown that it's able to work in this application, but maybe it needs a little bit more work to be implemented in a flight system. An engineering or a manufacturing gap is, yeah, we think we know how to solve this problem. We just need to throw some money at it in order to turn the crank a couple of times, and we'll get that figured out. A system level gap is, when we put these things together, we understand how they work. And an architectural showstopper is, we have no path forward. Nothing that we are aware of will provide a solution. And so again, keeping these things in mind as we're going through helps us figure out sort of what the scale of the gap is and how we need to move forward in order to close it. So the first place to start is with expected disturbances. What are things that are going to happen that are going to mess us up? And so the classical sources are things that we've known about for many years that affect instruments and telescopes of all kinds, including space telescopes. And we have environmentally induced, things that happens to us sitting out in space, and then we have system induced. So environmentally induced is going to be things like, thermal distortion from the solar flux. System induced is vibration from pointing your spacecraft. And what we really focused on is identifying potential new sources. What are all the little things we can think of that might mess us up? And then we did a back-of-the-envelope calculation to figure out, is this going to cause us a lot more than a picometer of error, about a picometer of error, or much less than a picometer of error? And that quick back-of-the-envelope calculation allows us to classify what things we can just put aside and not deal with, and what things need further investigation. And for the most part, a lot of the sources that we thought about, things like, is the gravitational interaction of 2 mirror segments going to cause a picometer of motion? Do we need to worry about charged particles flying around in space? Most of these things we were able to show is much less than a picometer. But there were 2 that we determined probably merit some further investigation. And so the first of these is Coulomb forces. So you have the telescope sitting out at Earth-Sun L2, so that's Lagrange point 2. That's the stable orbit that's about 1 million miles beyond Earth, away from the sun. That's where JWST is going to sit. And you have charged particles from the solar wind and other places coming around, and some of those particles are naturally going to be embedded in the mirrors. Glass is a pretty good insulator, and so you'll get those charges stuck in the mirrors, and then the propagation of the positive and negative charges will also cause a little bit of separation. So in theory, over the course of a year, you could get a surface figure error that looks something like this. That's the reason for that is because you have these light-weighted structures, and so if you, the back of the mirror is open, and so if you have these charged particles that are hitting it, then you might get greater concentrations in the ribs than you do on the face sheet. And so this is happening over the course of a year. This is not really something that's going to mess up our coronagraph observations over the course of minutes to hours. But the problem is if the figure of the primary mirror is moving, that means that you have a static correction on the DM that gets larger and larger and larger. And at some point, you have to worry about the dynamic range of that system to correct the static wavefront error. So it's not a stability problem, it's a static problem. The other thing about this is that if you look at this is 5 cycles across a mirror. And if you think about 10 mirrors across an aperture, this is 50 cycles per aperture. That light is going to be diffracted at very large angles and likely falls outside the coronagraph dark hole. You're not going to have a deformable mirror that can actuate this out. And so you don't bother having high contrast in that zone. So Coulomb forces may be something for a long level, but this is what we're calling the knowledge gap. We don't really know what the particle environment is out there. We don't really know how these charges are going to embed in glass or if this is the phenomenon, something to study in the future. The other one is micrometeoroid impacts. We have this open telescope architecture. We know that micrometeoroids are going to hit the mirrors, and especially for these meter class segments, you can imagine a micrometeoroid comes, hits a mirror, and maybe it vibrates, and it rings down. For longer observations, maybe that's okay, but for this high contrast coronagraph application, the perturbation that we calculated, if you assume a perfectly elastic collision between a micrometeoroid and a mirror, showed we could potentially get something more than a picometer. A perfectly elastic collision is probably not a great assumption. It was the place to start. And so we have flagged this as, again, a knowledge gap. We would need to look a little bit more into the impact physics, into the statistics of micrometeoroid density at the L2 environment. And so this one is also a knowledge gap. Stable structures. So these telescopes are made of composite structures that hold up the primary mirror, that support the secondary mirror out on struts, and have some connections to the sunshade in the spacecraft. So we evaluated state-of-the-art composite structures used for telescopes like JWST, and we looked at different parameters like how the thickness could vary as a function of coefficient of thermal expansion, moisture expansion, the plate thickness itself, what's the performance of the joints and adhesives that are used to join these two things together. And so in looking at that trade space and how we can improve the passive stability of structures, we looked at things like how you change the composite thickness, the operating temperature, bake out. A lot of these are related to coefficient of moisture expansion. You have water in the composite, and as it goes up on orbit, that water outgasses, and eventually you'll actually get shrinkage of the composite structure. And that's happening in an exponential time scale. So you put something up from being on Earth where it's humid, it's going to start drying out very fast. You're going to get a pretty high slope change, and then eventually it's going to level off. So you can do things like increase the temperature on orbit to essentially bake it out. This is what's done often in vacuum chambers on Earth as well. And changing your composite thickness also changes the amount of moisture that's trapped. And so you can tune how much dimensional change you're going to have for moisture expansion by varying some of these parameters and changing your CONOPS on orbit. We also looked at things like how you do the temperature control. So we know that for this large structure, if we want to maintain picometer stability, we need an active thermal control system. And so how you define those zones and whether you try to control at the individual segment level or at more of a low spatial frequency backplane is another thing that's in the trade space. So examples of some of the analysis that we did. Again, I mentioned that we tried to do a lot of parametric and sensitivity analysis so that this is applicable not only to LUVOIR, but other telescopes that might have a similar architecture. This is essentially looking at how much dry out time on orbit you need as a function of thickness. And these different contour lines essentially correspond to different amounts of allocation. So how much of the error budget is going to be taken up. So for thick parts that have low dry out times, these are going to consume a lot of the allocation. Thin parts up here will consume less. And so one of the things we determined is based on our ability to manufacture composites now, and based on a CONOPS of having some months of dry out time on orbit without doing an elevated bake, we determined that the composite thickness that you need is about 1.6 millimeters. And the question is that comparable to composites you've made in the past, or is it much different? The good news is it's in family with what's been done for JWST. So the composite itself, we can sort of define a set of operating parameters that will make the current state-of-the-art composite structures sufficiently stable for our needs. Good news. We also looked at things like fittings and adhesives. Those are usually much higher CTE materials than the composite itself. And so while the composite struts might not be changing dimension very quickly, adhesive or joints that are often metallic will be. And so you'll have sort of that larger contribution at these key points that, again, will perturb the mirrors more than you want. And so we looked at these as a function of temporal and spatial frequency, how are they changing with time, and assessed regimes where we think that we probably need to do some work to meet the allocations. And what this tells us is current joints and adhesives used for things like JWST probably aren't quite going to get the job done. So the takeaway message on stable structures is, for the most part, composite engineering, design, and manufacturing technology is of sufficient means to produce a credible backplane for LUVOIR. Good news. There's a couple of things that we think we need to work on. We need to be able to make measurements of coefficient of thermal and moisture expansion. And we call that an engineering gap because that's really about making sure that we can produce enough composite at a production rate to keep the costs down. Right now, we looked at if we, for the CTE uncertainty that we need for LUVOIR compared to what we had for JWST, we would have had to scrap 90% of the struts. It's not very cost effective, so if we have a better way of controlling the manufacturing process, which also requires metrology, we can bring those costs down and, again, move more towards a feasible architecture. CTE joint fittings and adhesives, same thing. We think that we have some work that we need to do. There's a path forward for that. That's kind of a time and money thing. Microdynamics and low energy propagation. This again goes back to the fact that we're worried about picometers and we're not really sure how very low strain energies propagate through these large structures. We've really only worried about it at the nanometer level. We have some ideas about how it should scale, but again, is that relevant? So that's a knowledge gap. There's some modeling and experimental work that needs to be done there. And then on the stable hinges and latches, this is because LUVOIR is a deployable telescope. So the wings fold out and then there's latch planes that lock them in place. Those are actually sources of pretty significant amount of dynamic instability when the wings flap and the latches kind of move back and forth. And so we have a couple ideas about how to redesign the latches so that they are more kinematic, they don't transmit as much strain energy, and so that one we're calling a mid-TRL gap. You know, we think we have some ideas about how to make it work. We've demonstrated some of these concepts, but it really needs to be proved for a LUVOIR or large segmented telescope specific application. All right. Stable mirrors, same process. We looked at state-of-the-art performance for, in this case, ULE, low expansion glass mirrors. We looked at things like how the surfaces deform as a function of thermal and dynamic perturbations. We looked at our mounting configurations, you know, how can we adjust our hexapods, how can we adjust the mount pads and the adhesives used to attach to the mirrors. Looking at dynamic load limits, allowable temperature limits, you know, how stable do these things need to be, what sort of level of control do we need. And the key trades in this space have to do with mirror material, a couple of different kinds of low expansion glass, potentially silicon carbide. Mirror mass, as you start to make the mirrors thicker and thicker, they're stiffer, they have a larger thermal mass, so they're not going to change their shape thermally as much, but it's more mass for the observatory, and that has space and launch vehicle implications. And then there's this mirror mounting approach. You know, do you use Invar bond pads? What kind of adhesive do you use? Is there some sort of other configuration than just three bond pads behind the strut? So what does that space look like, again, to increase the passive stability of the mirrors? And so, again, our analysis showed that for the most part, we don't have any major shortcomings in our current means of fabricating visible quality glass mirrors. An engineering gap, again, same thing as the structures, is material property measurements. Being able to make better measurements of not only the overall CTE, but also the CTE inhomogeneity will help our manufacturing process. And then for the mirror mounting, this is a mid-TRL gap. We think that there's a couple of other ways to adjust from this very simple mounting scheme that can help leverage that PSD-based error budget. So we talked about, you know, if you're looking at where the peaks show up in the dark hole, if you can imagine having some mounting scheme where you have more and more distributed mount pads, but without over-constraining the mirror, then you can potentially push that spatial frequency out to the right where you have a lot more room in the error budget. So there's some tricks we could potentially play there. One thing that we identified as a low TRL gap is right now we're assuming that we just need to control the 6th-off position of the mirrors, so the rigid body positions. However, it's possible that when we go back and we do all of this high-fidelity stop modeling, have a better understanding of the coronagraph and the thermal control systems, we say, oh my gosh, we need active control on the mirrors themselves. There are concepts for active mirrors, however, they are certainly not at the picometer stable level. And so if we got to the point where we need to actually do figure control on the mirrors themselves, that's a low TRL gap. But this is in italics because we think that that's pretty unlikely given what we know about the system sensitivities. Active sensing and control, we have the stable, the passively stable systems of the composite and the mirrors. Now this is about taking those and making sure that we can lock them back into place so that the passive stability isn't the only thing that's controlling the telescope. So we looked at things like what actuators do we have available to put on the backs of the mirrors. How can we leverage the heritage from ground-based telescopes that use edge sensors to sense the height between two mirrors relative to each other rather than just relying on some sort of optical throughput measurement? Again, we're looking in the coronagraph at very, very dim planet light. And so if we're just relying on the optics to tell us how the mirrors are moving with respect to each other, we're not going to be able to correct them fast enough to damp out all those disturbances. However, once you start actuating mirrors, you're also going to put forces and torques into them that are going to induce some instability and potentially figure error. So you have to make sure that you're not making the problem worse by actuating. And then there's higher level questions about control methodology. You have 120 segments, and they're all moving with respect to each other. How do you make sure that you're not driving them off into some, corner where the whole primary mirror is tilting? How do you incorporate a laser metrology system to serve as a global reference that then the edge sensors can sort of clean up the segments surrounding? So there's a bunch of sort of system level trades to be happening. Where do you do the control? Do you sense at the primary mirror and fix the mirrors? Or do you sense at the primary mirror and offload it to the deformable mirror in the coronagraph? So there's still a lot of options there about how you're implementing the control and what use of the information that you're making. And then also we know that we need a thermal sensing and control system as well. And in this case, we didn't do a lot of work on how to implement that system, but we assumed millikelvin level thermal control. That's been shown on very small pieces in well-controlled chambers. And so the question is, how does that extend to a large space structure? And so things we did, some dynamics modeling of the mirrors and the mounts. Again, very simplified picture to just get a sense of where the resonances are, what kind of forces we're putting into the mirrors, and what kind of surface figure implication that has. And a good old trade matrix, looking at what are our options for sensing segment-to-segment motion. We have edge sensors that can either use capacitive or inductive or optical methods. You can fly a very bright laser guide star out there. Instead of relying on the dim light from the planet, you can essentially put an artificial source. You can fly an interferometer at the center of curvature of the primary mirror. That's something people are thinking about. So, looking at not only what are our main performance metrics, things like resolution, range, bandwidth, but also the n-squared systems engineering impacts. What implications does this have on size, weight, power? Is this going to make my electronics extremely complicated? Am I going to be creating other thermal sources behind the primary mirror that now I have to worry about controlling? So a lot of this was done to identify what are the most promising candidates moving forward. And for the active sensing and control piece of the architecture, the bottom line is we actually do have some technologies here that are pretty low TRL that we do need to start developing soon if we're going to claim that this architecture is feasible in the next couple of decades. And so those areas are mostly related to segment sensing and control and system control methodology. We need to make an actuator that's capable of moving a picometer, but that also supports a 50 to 60 kilogram mirror on the ground for INT testing, obviously less on orbit. System control methodology, figuring out how all these control loops fit together, and then thermal sensing and control. So that one's a mid TRL instead of a low TRL because we've done it for some small optics, and so now it's again about making that leap from a very small and well-constrained system to a large and complex space structure. So that's all the things that are happening really on the telescope side of the sunshade, but something that's happening on the other side is the spacecraft. The spacecraft is pointing the telescope, it's maintaining its stability, and as it does that, all of its pointing mechanisms are going to cause dynamic frequency perturbations that are then propagating through the telescope. And so you've got A couple of options there. You can either make the spacecraft quieter by using microthrusters instead of control moment gyros, or you can isolate the system. And so really what we focused on here was not so much that part. There was actually another industry study that was looking at the dynamic systems, but looking at what's the implication on how well we need to control jitter in the telescope and specifically line of sight. So that's how the chief ray is moving around on the sky. And in most telescopes, there's a fine or fast steering mirror, depending on how the program names it. And what that's doing is the spacecraft keeps the telescope pointed at about the right spot, it moves around, and the fine steering mirror does that fine level of correction. But the problem is, as the telescope's moving and the fine steering mirror is correcting for it, you're actually getting beam walk on all the optics. It's not a lot. You're talking maybe nanometers or microns of beam walk motion, but we're talking about picometer stability. And so the question is, as that beam walks around on those other optics, what sorts of wavefront error is it adding? And there's a couple of different kinds of wavefront error it could be adding. There's sort of the ideal surface shape, and as the beam walks around, you're not sitting on exactly the right part of the astigmatism or something, and so that'll give you error. And also, the mirrors aren't made perfectly. You're going to have all of these manufacturing residuals, and the manufacturing residual in one patch of the mirror is going to look different than the other patch of the mirror. So you have sort of a cascading effect of what sorts of scales are you worrying about. So this was an analysis we did to see how much beam walk we can handle on each of the optics. And it varies per optics, not only because of the configuration. You're going to have beam walk that's pretty small on mirrors that are close to the pupil and pretty large on mirrors that are field or close to an image plane. And also the size of the mirror, the manufacturing residuals vary. You can make pretty smooth mirrors really small, but when you're starting to talk about those large primary and secondary mirror segments, even when you're talking about small beam walk, those are mid and high spatial frequency manufacturing residuals that you really can't neglect. And so again, our good old friend power spectral density helps us figure out how much beam walk we're going to get for specific types of polished surfaces, about how much energy is in each of those spatial frequencies, and thus we determine that we need to keep the line of sight stable to about 1 milli-arc-second in order to get a picometer of wavefront error. It is very small. And so again, we want to limit that beam walk and that line of sight drift by either using a low disturbance spacecraft or isolation and damping. And so the payload isolation, there are a couple of companies that have some ideas about how to do this. They've flown some of them, so they need to be adapted for LUVOIR. That's what we're calling an engineering gap. For our low disturbance pointing, that's a mid-TRL gap. We want to potentially look at if we can swap out those control moment gyros, which are basically spinning wheels that use momentum changes to point the observatory, to microthrusters, little things that are sort of jetting out small amounts of cold gas. Microthrusters are actually being used on the HabEx mission concept, but LUVOIR is really big, and it's hard to point the full observatory to all the targets that you need just using the microthrusters. So we're looking at some sort of hybrid approach. Can you do rough pointing with the CMGs, lock it in place, then turn on the microthrusters for your coronagraph observation? So that's, again, sort of in this, we know those pieces exist and have been used in these modes, but how do they work together for the LUVOIR application? And then there's finally low disturbance mechanisms. So things are moving on the telescope. You have the fine steering mirror moving around. You have actuation from the primary mirrors. What are things you can do to those mechanisms to try to minimize the amount of strain energy that they put back into the system? Okay, so now that we've gone through all of those different subsystems, we have the technology gap list, which really collates all of that information. Again, we have the main systems of active sensing and control, low disturbance architectures, structures and mirror mount structures, and then mirrors. And again, ranked all by the gap type. And so the low TRL gaps, the things we think are really important but need technology development immediately, are in the areas of things like segment sensing and control, system control methodology, and line of sight stability. Sort of the next level of concern, things that we think should probably be addressed pretty soon but aren't enabling for the architecture at the moment, are things like thermal sensing and control, stable joints and hinges, mirror mounting. I should say they are enabling for the architecture, but they aren't the tallest poles in the tent. Then we have a number of engineering and knowledge gaps, things that we need to continue to work on to show that they're feasible for the architecture or they're not a problem for picometers. Everything is pretty much a system level gap. No one has put all of these pieces together and shown that they work to the level required. So that's sort of a given at this point in our technology development phase. But the good news is that nothing's a showstopper. We haven't found any pieces where we go, we have no way to solve that problem. this telescope is broken. But if you look at the rest of this chart, there's no one silver bullet. It's not if you just do this one thing, all of a sudden everything locks into place. And that's really the goal of the systems engineering too, is you don't want to necessarily have one thing that carries the entire risk for the architecture. You want to make reasonable gains in a number of places in order to make sure that your technology development, if something doesn't work out the way you planned, maybe you have other areas that you can make it up. But also, if for some reason on orbit your performance in one area degrades a little bit, it's more of a graceful degradation. You haven't lost the critical function of the telescope, and you can still do your science. Okay, so we've identified the technologies that we need in all of these areas. How do we get them to where we need them to be? And so the general philosophy is you start by the smallest building blocks. You increase the component TRL. So that's things like building an actuator or building a composite joint that's more stable. Then you start putting those things together and you start characterizing the interaction. What happens when I take this new mirror mount with this well-characterized mirror material and I add edge sensors on it and I let them move around? And as you start to build that fidelity up and see how all these things interact, and you say, well, my control loop here really needs to run faster, or, oh, my passive stability here is better than I thought it was, I can turn this knob down. Now you're really talking about increasing the system TRL. You really know how all the things are being put together, you have a better understanding of the requirements, and you're not making anything work much harder than it needs to. For LUVOIR specifically, the way that this looks is starting with things like demonstrating components of edge sensors, a picometer actuator, a thermal control system, and again, getting all those pieces together. Then nominally, we think you want to build 2 test beds. One is a mirror cell test bed, so that would be like a little piece of a backplane, the mounts, the actuators, the mirror, the thermal control system, and that would tell you sort of for the optic mechanics perspective how all these things are interacting and what level of stability you're achieving. Then on the other side, we think you should build a control architecture test bed, where you don't really worry about the fidelity of the optics and the structures as much. Now you're testing out, how does my laser metrology system interact with my edge sensor system? How are those bandwidths being defined? Am I getting noise that's somehow propagating through the system that's causing a larger instability? And so the point of these test beds is you want to add fidelity where it's going to serve your purpose, and not add it where it's going to just increase your cost. You can't go off and just build a subscale LUVOIR. You have to break it down into these pieces. And so focusing on the optomechanics and the control architecture we think is a reasonable next step. Then once you do all of those things, now you need to start building something that looks like the observatory. So you start with a primary mirror demo, a couple of segments, all the key pieces, the control methodology, and you build that up. Then you want to make a telescope, so you add a secondary mirror. Now you can look at things like how that alignment's working out, are the struts giving you the stability that you need? And then finally, ultimately, you want to put a coronagraph behind it. Is the telescope stability really giving you what you need for the coronagraph? And is all of that work we did up front with that PSD-based error budgeting, really what we're seeing in the hardware? And so in addition to doing all of these demonstrations that really get at what is what we want to build for LUVOIR, you also have to have a lot of investment in facilities, and the coronagraph, and the spacecraft, and things like that are all happening in parallel. Again, no silver bullet. All of these things need to advance together, and we really want to advance them in parallel so that when we learn things about one, they can be used over in another place to either tighten performance where it's needed or loosen requirements to make the technology development easier. So our key takeaways from phase 1. Our ultra-stable architecture is a system of systems. There's a lot of moving parts, and we can really trade off between them if we have a good understanding of how they interact. Not all modes require picometer stability. As we learned, these segment-level modes are most damaging to the coronagraph, and these Hertz temporal modes are also the biggest drivers of contrast instability. Things that are happening more slowly or on larger pupil scales, you have a lot of control loops, the coronagraph is less sensitive. Things that are happening at higher scales, again, either outside the dark hole because they're very high frequency, or they're happening so fast that they're essentially creating a blur that can be subtracted out of the image afterward. Our PSD-based approach to stability budgets can provide potentially additional relief in our error budgeting with respect to the RSS approach. Thinking about the coronagraph dark hole as a 2D problem and how our energy is distributed might make our lives easier. And finally, our lowest TRL technologies are related to a lot of the active control systems, segment sensing and control, thermal control, and most of the mid-TRL technologies are related to improving the passive stability of the structures and the mirrors, which makes the control problem easier, so it's worth pushing on those things. But they're sort of already operating in a regime that we think is about what we need for LUVOIR. And another thing to point out is picometer is a scary word. I've gotten used to it, so maybe I don't seem as freaked out. But picometer sensing and control has been demonstrated. There are commercial actuators that you can buy that operate in the tens of picometer range. And we have some heritage capacitive sensors at Ball Aerospace that have shown 5 picometer-ish noise. The problem is that none of these are really in a configuration that's appropriate for a space telescope. So again, this is, sort of the TRL 2.3. We're not creating new physics. We're not saying no one has ever seen a picometer. But what we're saying is, here are the approaches that you need to take, but we really need to think about how this could be implemented for this application. All right, systems engineering. As you can see, it's a long and complex process and one that is never completed. But we finished that phase last year, and now we're moving into our phase 2, where we're starting to think about what kind of hardware we need to build to continue moving down this path of TRL maturation. So based on that technology gap list and the roadmap that I just showed, we came up with 10 key technologies that we're going to focus on in this next phase, nominally grouped into active and passive technologies. So again, this is things like picometer actuation, picometer edge sensing and metrology, thermal sensing and control, microthruster precision pointing, all the active pieces that we have to fix instability in the telescope. And then on the passive side, again, because developing these is important in parallel with the active technologies, because the passive stability is sort of going to tell you what your capture range is for your active system, and the performance of your active systems tells you what needs to be taken care of by the passive system. So that's looking at things like how can we improve our mirror mounting to have lower thermal distortion, how do we model damping in large space structures to address these nanostrain levels, and how do we redesign latches so that they're, again, minimizing that dynamic strain energy as it's propagating through the telescope. And of course, even though we're talking about building hardware, we can't forget that stability budgets and the requirements set by the coronagraph are still our guiding principle and telling us what we need to do for all of these things as they flow down. And as we continue to improve, again, our performance analysis, continue to push on coronagraph designs and modeling, we'll get a better understanding of what the requirements really are. So even the top level requirements themselves really are not a static quantity at this phase in the program. And so really what we did in picking these was to try to identify the things that were most enabling for the architecture, lowest TRL, and thus had the most immediate need for technology development. So we kicked this program off about 2 months ago, so I don't have any pretty hardware pictures for you yet. But the kinds of things that we're looking at are things like taking a 2-stage JWST actuator and adding a third ultra-fine stage on top. The way that the JWST actuators are designed right now is you can actually only move one at a time. You can imagine that's probably not going to work if we're talking about Hertz level corrections. And so this third stage that we're adding on top is really more of a servo loop. So you want to start running those actuators really in real time with a control system that can support that bandwidth. On the edge sensor side of the house, looking at things like, can we just put 2 large capacitive plates behind the mirrors, one attached to each segment, and just look at the change in capacitance as the mirrors move with respect to each other? How does that work? Or if we have an optical truss, can we actually just have distance measuring interferometers in some configuration between the segments? What are the trades between those two? What sensitivities do they have to the various degrees of freedom? We care a lot more about out-of-plane motion than in-plane motion. And so the geometry of those two affects the sensitivity to those different degrees of freedom. On the passive technology side of the house, we have composite tubes. Can we do things like replace these metallic elements with other composites? If we have to bond them on, what does the adhesive do to that? Can we get things out of the load paths so that we're not having the dynamic strain energy propagating through those softer surfaces? Sort of what are ways to design a better latch? And then on the metrology side of the house, we're talking about things that are being picometer stable. We need to be able to measure dimensions to picometers. And so we're looking at how can we measure CTE and CME at very low rates in composites that will give us that picometer level stability. So that's all what we're in progress on right now. And so looking ahead to phase 3, this is the technology maturation of the system. For NASA programs, especially for flagships, they want you to have all of your key technologies at TRL 6. So that's proven in a hardware configuration in a relevant environment by your preliminary design review. And for the LUVOIR nominal schedule, that's in 2032. LUVOIR's schedule is launching in 2039. So decadal survey is really more like a 2-decadal survey, but that's neither here nor there. However, if you can demonstrate technology development earlier, you can potentially identify risks earlier, have additional mitigation plans, and actually compress the schedule and thus the cost of your mission. If you're doing things really slowly and you have to sort of spread that out over time, you have standing army costs. All of these people are standing around, waiting for these tests to get done, and that increases the overall cost of the mission. So the LUVOIR team actually said, all right, well, if we can get all of these enabling technologies to TRL 6 by phase A in 2025, that's actually going to really help reduce our costs over the lifetime of the mission. And so thinking about all of these component level demonstrations and how you start putting them together, for JWST what was done is they built a 1/6 scale model called the Testbed Telescope. This is actually currently at Ball Aerospace. And it had high fidelity actuators, control mechanisms, mirror configuration, and things like that. And basically, the idea of this test bed was to prove out that once the telescope launched, unfolded, we could align it on orbit to its requirements. And so in order to prove TRL 6 that you could align this, it's not a Code 5 simulation, it's not an FEA simulation, it's building a $50 million piece of hardware. For LUVOIR, with a much larger aperture, more segments, more control systems, you're talking about a pretty big effort, but that's really where you're headed in order to prove that, again, all of these things work together to the level that they need to. So that's a segmented primary mirror, that's a secondary mirror out on struts, probably with a laser metrology system, all of the actuators and edge sensors, a thermal control system, a coronagraph, and some sort of spacecraft simulator with the vibration isolation. So ultimately, that's what it's going to take before we feel like we have confidence to really start building not before we start building, but sort of in parallel, building the full system and making sure that, again, there aren't any of these little gotchas that, if only we had built hardware, if only we'd done the Pathfinder, we would have known. Right, a few words on Ball Aerospace before I finish up. So I've been telling you a lot about our flagship astrophysics work, but one of the great things about Ball is we will do science at any scale. So we do the large flagship missions, we'll do the smaller explorer missions, and we will also talk to you about a CubeSat idea. So we like to partner with universities. We want to hear people's ideas. We're working with a couple of people here already. We're providing spacecraft for Chris Walker for Gusto, and a couple of other, Erica Hamden for Hyperion as well. So if you think that Ball could be a potential partner for technology development, for a mission idea, please keep us in mind. We also do a lot more than astrophysics, but that's what I'm here to talk about. So thanks. I want to